Hello, my name is Parker Duncan, and I will be presenting an executive summary on resilience assessment of urban connected infrastructure networks, a research article by Liu, Huang, and Long published in 2025. This research directly addresses the National Academy of Engineering's grand challenge to restore and improve urban infrastructure. The grand challenge, restore and improve urban infrastructure. The problem this faces is that urban infrastructure systems are deeply interconnected. When one system fails, disruptions cascade rapidly into others. To expand on that a little bit, uh, the problem this research addresses is critical to modern cities. Urban infrastructure systems, including transportation, water supply, energy distribution, and communication networks, are deeply interconnected. When one system experiences a disruption, failures can rapidly cascade into other systems, producing large scale impacts on public safety, economic activity, and overall city functionality. Traditional approaches to infrastructure assessment have examined these systems independently. For example, evaluating a transportation system without considering its reliance on electrical power or communication networks. However, this siloed approach fails to represent the real behavior of cities where infrastructure networks are tightly coupled. A power grid disruption can disable traffic systems, which then affects transportation performance. Similarly, communication failures can limit emergency services, slowing down recovery efforts. Uh, a little overview uh, to address these limitations. Liu, Huang, and Long introduce a multi-layered connected network model that represents multiple infrastructure systems simultaneously and analyzes how failures propagate between them. The primary goal of their research is to create a resilience assessment framework that captures the full life cycle of infrastructure performance during disruptive events. The framework evaluates how well uh, uh, complex infrastructure models networks can withstand, absorb, and recover from disruptions. By providing quantitative metrics, the researchers give engineers a tool for comparing different infrastructure configurations and identifying system weaknesses before failures occur. Now, to kind of explain the multi-layer network a little bit better, the authors represent infrastructure systems as interconnected layers with a single network. Each layer contains nodes and links that correspond to specific infrastructure components, such as power substations, water pipelines, and transportation routes. Uh, Now, the three phases of resilience, the authors define resilience through three distinct phases. First, resistance, which is the system's capacity to prevent or limit initial disruption. Second, absorption, which measures how well the network can continue functioning despite failures. And third, recovery, which captures the speed and completeness with which the system returns to normal operation. The researchers conducted an extensive simulation and experiments to test how different disruptions can affect urban connected infrastructure networks. They examined three types of failure scenarios: targeted attacks on key nodes, random failures, and spatially clustered hazards such as natural disasters. The results revealed several important findings. Networks with stronger independencies are significantly more vulnerable to cascading failures, especially when high centrality nodes are disrupted. In multi-layer systems, removing a small number of critical nodes can trigger widespread system collapse, reducing overall infrastructure performance, sustainability, uh, and uh, and it causes substantially more issues than would occur in isolated networks. The this highlights the critical importance of identifying and protecting components that serve as cross-layer hubs or dependency points. So, how the networks responded to the disruptions. A key finding was that infrastructure networks respond very differently depending on the type of disruption. Random failures produce gradual performance degradation, where the system slowly loses capability over time. In contrast, targeted failures can abrupt system collapse, leading to rapid catastrophic failure across networks. This model also demonstrates that recovery strategies significantly influence resilience outcomes. Three strategies proved particularly effective were rapid restoration of key nodes, reinforcement of interlayer connectivity, and diversification of dependency paths. The authors emphasize that resilience is not solely about preventing failures, but also about designing systems that recover quickly and effectively after disruption occurs. Some engineering applications and solutions on how to improve resilience. Uh, uh, from an engineering perspective, this framework provides valuable insights into how urban infrastructure should be planned and managed. The city the study suggests that resilience can be improved through several approaches, reducing excessive dependence between infrastructure layers, increasing redundancy in critical components, and applying protection strategies that focus on nodes with high interconnection strength. For cities with aging infrastructure, this approach allows decision makers to prioritize upgrades that deliver the greatest resistant gains. The method presented in the article uh, the method presented in the article support risk-informed planning, guide investment strategies, and improve emergency responses preparation. Engineers can use these tools to make data-driven decisions about where to allocate limited resources for maximum resilience improvement. Some societal impacts and importance. The societal impact of this research is significant. As urban populations continue to grow and climate related disasters become more frequent, the vulnerability of interconnected infrastructure systems poses increasing risks to public health, safety, and economic stability. Consider the cascading effects of power outages. This can simultaneously disable hospitals, water treatment facilities, and emergency communication systems. Transportation failures can prevent evacuation during emergencies and delay delivery of critical supplies. The cascading nature of these failures means that relatively small initial disruptions can escalate into citywide crises affecting millions of residents. This framework helps engineers design infrastructure that protects communities from these cascading risks. Um, some tools that engineers gain are the practical tools for designing robust urban systems, that being, communications and different ways to plan around these urban systems, methods to identify and protect critical vulnerabilities, that being weak points, or maybe it's an older portion of the city's infrastructure that needs to be watched very carefully. Frameworks for integrated planning and targeted reinforcement. This also goes back to identifying to protect critical vulnerabilities. It's just to keep a better eye on things. They may have a better mindset about monitoring older water lines or older power lines or substations. and strategies for rapid recovery after disruptions. This could be, this is, more of what do we do after something has happened, and we we can understand what to do afterwards. A key takeaway from this is that this research provides a scientifically grounded, system level approach to infrastructure resilience that acknowledges the interconnected nature of modern cities. Thank you.